Welcome back to The Sleepy Geographer, a quiet corner where we explore the world not in a rush, but with a gentle curiosity. Tonight we settle in for a story about the planet's most sudden and powerful language. A story written not in words, but in tremors. This is the story of earthquakes. Before we begin, I wonder if you can feel it. As you sit there, wherever you are in the world, the ground beneath you feels like the very definition of solidity. It is the stage upon which our lives play out, unchanging, permanent, the one thing we can always rely on. But this is an illusion. Beneath that apparent stillness, our Earth is anything but asleep. It is alive, it breathes, it stirs with a restless energy that has been simmering since the planet's fiery birth. What we perceive as solid ground is merely a thin, fragile skin, a crust adrift on a vast, slow-moving sea of rock. The planet has a pulse, a deep, rhythmic beat that manifests not in a heartbeat, but in a shudder, a tremor, a sudden, violent adjustment deep within. This pulse is the earthquake. For centuries we saw them as punishments from gods or as random acts of nature's fury, but they are neither. They are simply the Earth's way of speaking, of moving, of releasing the immense pressure that builds from its own incredible inner fire. In this series, we will listen to that pulse. We will journey from the familiar stillness of our surface world down into the unimaginable heat and pressure of the Earth's interior, where forces beyond our comprehension set the stage for drama. We will learn how the slow, relentless drift of continents, adrift no faster than your fingernails grow, can culminate in seconds of world-shattering power. This is not just a tale of destruction, though that is a part of it. It is a story of connection, a reminder that the ground beneath your feet is connected to every other part of this dynamic, living system. A quake in the ocean floor can send a wave across an entire ocean. A shift along one fault line can redistribute stress to another, thousands of miles away. We will explore the tools we use to listen to this planetary whisper, the seismographs that translate the Earth's deepest groans into delicate lines on a page. We will meet the brave minds who work to understand this power, not to stop it, for that is beyond us, but to live alongside it with greater wisdom and respect. So, find a comfortable place to rest. Let us set aside any fear and replace it with wonder. For the next little while, we will be quiet listeners to the greatest story ever told. A story written in stone and force, a narrative of a planet that is, and always will be, profoundly, beautifully, and restlessly alive. To understand the tremor, we must first understand the slumbering giant. We must look past the illusion of solidity and see our world for what it truly is. Not a single, solid rock, but a beautiful, dynamic assembly of layers. Imagine, if you will, the most intricate cake you've ever seen. Each layer has its own composition, its own texture, its own role to play in the whole. Our Earth is this cosmic cake, baked over billions of years, and its layers hold the secret to the planet's pulse. The outermost layer, the one we walk upon, is the crust. This is the thinnest, most fragile layer of all. If we were to scale our planet down to the size of an apple, the crust would be no thicker than its shimmering skin. Yet, upon this delicate shell, every human story has unfolded. Every mountain range, every ocean trench, every city is etched into this thin veneer. It is broken into enormous pieces like a cracked eggshell, which we call tectonic plates, and these plates are adrift. Beneath this brittle skin lies the mantle. This is the Earth's largest layer, a vast, thick region of solid rock. But here's the mystery. It's solid, yet it flows. Imagine a great block of honey or a stick of warm tar. To the touch it seems solid, but leave it for long enough and you will see it slowly, imperceptibly creep and deform. The mantle behaves in this same patient, viscous way. Heated from below and cooled from above, it moves in great convective circles over millions of years. This slow, creeping dance is the engine that drives the plates above it. This is the restlessness that sets the stage for everything to come. And, deeper still, we find the core. Our journey ends here, not because we've reached the limit of our curiosity, but because the conditions defy almost all imagination. The core is divided into two realms. The outer core is a swirling ocean of liquid iron and nickel, a frantic dynamo whose motion generates the Earth's protective magnetic field. Without this hidden shield, solar winds would strip away our atmosphere, and life as we know it would not exist. And at the very heart of it all, the inner core, a sphere of solid iron under such immense pressure that it remains solid despite temperatures that rival the surface of the sun. It is a forge, a heart of incredible power, locked away in the deepest dark. So, when we feel the ground shake, we are feeling a message from this layered world. A stress that began in the slow convective sigh of the mantle, translated into a sudden snap in the brittle crust above. The earthquake is not a random event. It is a conversation between the layers, a signal from the depths, reminding us that we live on the thin, cool skin of a profoundly hot and active world. We have met the layers of our planetary cake, the thin, brittle crust and the slowly churning mantle below. But this is only half the story, for the crust is not a continuous shell, it is fragmented, and these fragments are in motion. This is the great discovery, the unifying theory that taught us to speak the language of our restless planet, the theory of plate tectonics. Imagine that cracked eggshell of the crust, but broken into a dozen or so major pieces and a few more, smaller ones. These are tectonic plates, and they are not merely floating, they are rafting. They glide across the surface of the Earth, carried by the immense, slow-moving currents of the mantle below. Their pace is almost unimaginably slow, moving only a few centimeters each year, about the same speed your fingernails grow. In a single human lifetime, their movement is negligible. But over millions of years, this slow dance rearranges the entire face of the planet. Once, all the world's continents were joined together in a single supercontinent called Pangaea. You can still see the evidence yourself. Look at a map. See how the eastern bulge of South America seems to fit perfectly into the westward curve of Africa. That is no coincidence. It is a fossil imprint of a time when they were one. The plates have been pulling them apart ever since, opening the Atlantic Ocean like a zipper between them, and they continue to drift apart to this day. This movement is the engine of it all. It is the reason for most of the world's mountains, earthquakes, and volcanoes. Where these giant plates meet at their boundaries, the Earth reveals its dynamic nature. It is here that the planet's skin is being created, destroyed, and transformed. Some plates pull away from one another, a process we call divergence. In the gaps they create, hot magma from the mantle rises up to fill the void, cooling to form brand new crust. This is how ocean basins are born and how mid-ocean ridges, the longest mountain ranges on Earth, are built, all hidden beneath the waves. Other plates collide in a tremendous, slow-motion crash we call convergence. And this is where the real drama unfolds. If one plate is denser, it will dive beneath the other in a process called subduction, bending back into the mantle from whence it came. This is how ocean trenches, the deepest parts of the sea, are formed. And if two continents meet head-on, neither wants to dive down, so they crumple, they fold, they thrust upward in a colossal wreck of rock, raising mighty mountain ranges like the Himalayas mile by mile. The plates are the actors on the global stage. Their interactions are the plot. And the earthquakes, they are the moments of high drama in this epic multi-million-year story. They are the sound of the engine shifting gear, the creak and groan of these colossal rafts as they jostle and grind against one another in their patient, unstoppable journey. We have met the players, the great tectonic plates adrift on their slow, ceaseless journeys. But a journey implies a destination, and for these continental rafts, their paths are destined to cross. The true drama of our planet unfolds not in the quiet centers of these plates, but at their edges. It is at these boundaries where giants meet that the Earth's crust is born, destroyed, and transformed. There are three ways these behemoths interact, three types of conversations they can have, each with its own unique language and landscape. First, there is the conversation of creation. This happens at divergent boundaries. Here, two plates are pulling away from one another, stretching the crust between them. It is a gentle, if persistent, parting. As they separate, the mantle below wells up to fill the gap, melting from the release of pressure and cooling to form brand new crust. On the ocean floor, this process builds immense undersea mountain ranges called mid-ocean ridges, the longest continuous mountain chains on Earth. On continents, this stretching can tear land apart, forming great rift valleys like the one slowly opening in East Africa. Here, the planet is quite literally ripping itself apart to make something new. Then there is the conversation of collision and destruction. This is the convergent boundary. It is the most dramatic of meetings, a slow-motion crash of unimaginable force. When two plates move toward each other, one must yield. Often, a denser oceanic plate will dive beneath a lighter continental plate, bending back into the mantle in a process called subduction. This descent creates deep ocean trenches and fuels violent volcanoes on the overriding plate, like those that ring the Pacific. But when two continents collide, neither will sink. Instead, they crumple, they fold, they thrust ancient seafloors skyward, slowly, painstakingly building towering mountain ranges. The Himalayas are the product of such a colossal embrace, a wrinkle in the Earth's skin formed where India met Asia. Finally, there is the conversation of friction. At transform boundaries, plates neither create nor destroy. They simply grind past one another. It is like two immense hands sliding sideways against each other. For long stretches they may stick, locked together by friction as pressure builds. Then, in a sudden, violent release, they lurch forward. This is the source of some of the most famous and powerful earthquakes. The San Andreas Fault in California is a classic transform boundary, where the Pacific Plate slides northward against the North American Plate. It is a place of lateral stress, where the Earth speaks not with a roar of creation or collision, but with the sharp, grating shudder of slip and strain. These boundaries are the active seams of our planet. Every mountain, every trench, every volcano, and most earthquakes are simply the visible and audible signs of these endless conversations between giants. We have mapped the stage, the layered Earth, and met the actors, the drifting plates. We know where they meet at their divergent, convergent, and transform boundaries. But what is the script for the drama that unfolds there? It is written in the silent, invisible language of stress and strain. Imagine a simple wooden stick. If you hold it between your hands and push your palms together, you are applying a compressional stress. The stick feels this pressure. It might bow outward, slightly, accommodating the force. This is strain, the change in shape caused by the stress. Now imagine pulling on the ends of that same stick. This is tensional stress, stretching it, making it just a little bit longer, a little bit thinner. This is exactly what happens to the vast solid rock of the Earth's crust. The tectonic plates are in constant motion, and as they push, pull, and slide past one another, they exert these immense stresses on the rock at their boundaries. For thousands, even millions of years, the rock withstands it. It is remarkably strong. It bends, it folds, it stretches, it compresses. It stores the energy of that motion like a spring being wound, tighter and tighter. This bending is not a sudden act, but a profoundly slow one. Rock, under enough pressure and over enough time, can actually flow and deform without breaking, like warm toffee or a glacier of stone. Geologists call this ductile deformation. It's what creates the great graceful folds seen in mountains. Ranges, swathes of rock that have been warped into colossal waves, frozen in time, but rock, even deep underground, has its limits. Closer to the surface, where it is colder and more brittle, it cannot flow so easily. Here it responds to stress. Differently, it resists, it cracks, it faults, but still it holds. The stress continues to build and the strain increases. Friction along fault lines locks them in place, acting like a keystone, holding everything together even as the pressure mounts to incredible levels. This is the long, silent prelude to an earthquake. It is a story of immense patience and accumulating force. The landscape around a fault may seem utterly still, but it is a scene of arrested motion, of potential energy waiting to be unleashed. The ground itself is under strain, storing every bit of energy imparted by the drifting plates, like a drawn bowstring that cannot be held forever. The rock does not want to break. It is simply being asked to hold more than it can bear. It endures this immense pressure for centuries, until one day the stress finally exceeds the strength of the rock and the power of friction holding the fault together. And that is when the silence ends. In the long, silent prelude of building strain, there is a moment of no return. A threshold is crossed. The strength of the rock, its ability to withstand the immense stress, is finally overcome. The friction that locked the fault line in place for centuries suddenly fails. This moment, this precise instant of fracture, is the beginning of the earthquake. It does not begin across a vast area all at once. It starts at a single point, deep within the earth, along the fault plane. One small patch of rock gives way. This initial rupture is like the first domino falling, or that single drop striking the water. The exact point within the earth where this rupture initiates is called the hypocenter, or sometimes the focus. This is the true birthplace of the earthquake, the hidden spark that ignites the event. It is here, often many kilometers below the surface, that the stored energy is first unleashed. As the rock on one side of the fault suddenly lurches past the other, the energy released at the hypocenter radiates outward in all directions through the solid rock, like ripples from that drop in the pond. These are seismic waves. They travel upward, downward, and sideways at incredible speeds. In a matter of seconds, these waves race toward the surface. Now picture a point directly above the hypocenter, on the Earth's surface, directly up on the ground where someone might be standing. This point on the map is called the epicenter. It is the geographical address of the earthquake, the place we mark on our charts. It is crucial to understand this distinction. The hypocenter is the source buried deep in the Earth's crust. Epicenter is its shadow on the surface. Typically, the strongest shaking is felt at the epicenter because it is the shortest, most direct path for the seismic waves to travel. But the story of the shaking is rarely that simple. The geology of the area can dramatically alter the intensity. Loose, wet sediments like those in river valleys or reclaimed land can amplify the waves, making the shaking feel much more violent than it would on solid bedrock miles away. This is why two towns the same distance from the epicenter can experience the earthquake so differently. So when the ground begins to tremble, it is the echo of that singular point of failure deep below. The hypocenter speaks, and the epicenter is the first place to hear its voice. The rupture then propagates along the fault line from the hypocenter, sometimes for hundreds of kilometers, unzipping the Earth's crust in a wave of catastrophic motion. The depth of the hypocenter is what ultimately writes the character of the earthquake we feel. A shallow hypocenter, just a few kilometers down, means the waves have a very short journey to the surface. Their energy is still intense, concentrated, and often more destructive to the area immediately around the epicenter. A deep hypocenter, perhaps hundreds of kilometers down, allows the waves to spread out and weaken on their long journey upward. The shaking at the surface may be felt over a much wider area, but it is often less intense at any single point. The break has occurred. The waves are rushing outward, and on the surface, in the quiet town, the stillness is about to end. The rupture has begun. The fault has slipped. Deep within the earth, at the hypocenter, a tremendous amount of stored energy is released in an instant. But energy cannot simply vanish. It must travel. It radiates out from the break like sound from a bell, or ripples from a stone tossed into a pond. These vibrations are seismic waves, the language of the earthquake itself, and they come in different forms, each with its own character and consequence. The first to arrive are the P waves, primary waves. They are the messengers, the swift heralds of the coming event. P waves are compressional waves. They move through the earth much like a sound wave moves through air, by alternately compressing and expanding the rock in the same direction they are traveling. Think of a slinky. Push and pull one end, and a pulse of compressed coils travels down its length. This means P waves can travel through both solid rock and liquid layers like the outer core. They are the fastest of the seismic waves, and while they are usually not the most damaging, their arrival is the first tangible sign that something profound has happened deep below. To someone on the surface, a P wave might feel like a sudden sharp jolt or a deep sonic boom that seems to come from everywhere at once. Following close behind, moving at about half the speed, come the S waves, secondary waves. These are the real workhorses of the shaking. S waves are shear waves. Instead of compressing, they move the ground perpendicular to their direction of travel in a shearing, side-to-side or up-and-down motion. Imagine shaking a rope up and down. A wave travels along it, but the rope itself moves at right angles to that wave. This shearing motion is far more effective at shaking the foundations of structures. Crucially, S waves cannot travel through liquids. Their inability to pass through the Earth's outer core was our first great clue to its liquid nature. When S waves arrive, the gentle jolting of the P waves gives way to the true, violent rolling and shaking that defines an earthquake for most people. But the story does not end there. When these body waves, the P and S waves, reach the Earth's surface, they interact with it to generate a third, more complex set of waves, surface waves. These are the slowest of all, but they are often the most destructive. They travel just under the surface like waves in the ocean, but rolling through the solid ground. They have a longer wavelength and produce a pronounced rolling or swaying motion, like being on a boat at sea. It is these waves that cause the ground to ripple visibly that are particularly effective at toppling buildings and crumbling infrastructure as they shake the ground from side to side with a powerful, prolonged motion. So the experience of an earthquake is a layered one. First, a sharp jolt, P wave. Then a period of intense, violent shaking, S wave. And finally, the lasting rolling sway that seems to go on and on, surface waves. Each wave is a different expression of the same energy, a different verse in the Earth's powerful poem of release. There is a moment in the heart of an earthquake that is not defined by chaos but by a question. It is a fleeting, subtle instant that often goes unnoticed, a whisper before the shout. This is the arrival of the P-wave, the first herald of the deep rupture. If you have never experienced it, imagine this. You are sitting in a quiet room. Everything is still. And then a sound, but not a sound you can place. It is a low, deep rumble that seems to come from nowhere and everywhere at once. It is not yet a shaking. It is a vibration that travels up through the foundations of your building and into your bones. Or perhaps you feel a sudden, sharp jolt, as if a very heavy piece of furniture was dropped in the room above you. A pendulum on a clock might swing erratically for a single pass. The water in a glass might shiver with a single concentric ripple. This is the primary wave, the P wave. It is the fastest of the seismic waves, and so it is the first to arrive, the first sign that the Earth has spoken miles below your feet. Its motion is compressional. It pushes and pulls the rock and everything built upon it in the same direction it is traveling. This is why its feeling is so often described as a jolt or a bang. It is a wave of pressure, a sonic boom traveling through solid ground. For those who have lived through quakes, this moment is instantly, intuitively recognizable. It is a sensory trigger that sends a jolt of adrenaline as potent as any sound. It is the planet's tap on the shoulder. A dog might lift its head and whimper seconds before a human feels anything, its sensitive feet detecting those initial vibrations. There is a strange, suspended silence that can follow that first jolt, a second or two of utter confusion and dawning realization. The mind races to categorize the sensation. Was that a truck? A large animal, but the deep, subsonic quality of it feels wrong. It feels geological. This brief window, this gift of a few seconds between the P wave's arrival and the more destructive S waves, is the basis for modern early warning systems. Sensitive seismometers can detect these fast-moving P waves deep underground, calculate the earthquake's likely strength, and send out alerts that can travel faster than the seismic waves themselves. A phone might buzz, a siren might blare, giving precious moments to brace, to stop a train, to seek shelter. The P wave is the tremor of anticipation. It is the subtle change in pressure that makes the air itself feel different. It is the deep, quiet breath the earth takes before it begins to roar. It is not the earthquake itself, but its shadow. And in that shadow, for those who know how to listen, lies a warning. The warning has passed. The deep initial jolt of the P wave, that subtle herald, has arrived and gone. And for a heartbeat, there is a pause, a breath, a moment of eerie, suspended silence where the world seems to hold itself together. Then, the S waves hit. If the P wave was a sharp knock at the door, the secondary wave is the door being kicked off its hinges. It arrives with a transformative violence. The initial jolt gives way to a brutal, shearing motion. This is no longer a push or a pull. This is the ground being whipped sideways, up and down in a chaotic, wrenching dance. The S-wave's motion is perpendicular to its direction of travel. It doesn't compress the ground, it shreds it. This is the destructive heart of the earthquake. It is this violent swaying that tests the integrity of everything we have built. Buildings are designed to handle vertical forces, the constant push of gravity. But the S-wave's lateral assault is an unnatural sideways force that their structures are not naturally braced against. The ground moves one way and the building's foundation moves with it, but its upper stories lag behind, then whip back, creating a terrifying torsion that can snap support columns, collapse walls, and rupture gas lines. The sound changes. The deep rumble is now joined by the cacophony of the human world failing, the scream of twisting steel, the explosive shatter of glass, the percussive crash of masonry hitting the street. Inside a building, the feeling is not of being jolted, but of being adrift on a violent, unpredictable sea. The floor heaves and rolls. It becomes impossible to stand. The world outside the window becomes a dizzying, jostling blur. S-waves are shear waves, and they live up to their name. They are the planet's shears, slicing through the stability of the surface world. Their longer period of shaking, often lasting for what feels like an eternity, allows the damage to compound. A structure might withstand the first few seconds. But as the shaking continues, cracks propagate, weaknesses are exposed, and failures begin to cascade. This is the wave that turns the abstract concept of an earthquake into a visceral, terrifying reality. It is the embodiment of the energy release at the hypocenter, finally expressing its full, brutal force upon the landscape. It translates the deep, slow grind of tectonic plates into a language of immediate and utter chaos that every living thing can understand in its gut. And then, as suddenly as it began, the most violent shaking subsides. The S-wave's energy passes through. But the event is not over, for in the wake of this violent sway, something else often arrives, a long, slow, rolling motion that can be just as destructive. The earthquake has spoken its loudest verse, but it has not yet fallen silent. The violent, shearing assault of the S-waves passes, but the earthquake is not finished speaking. In the eerie relative quiet that follows the peak of the shaking, a new, more insidious motion often takes hold. The ground does not grow still. Instead, it begins to roll, to swell and fall with a long, slow, sickening undulation. This is the arrival of the surface waves, the final and often most destructive act of the seismic performance. These waves are the children of the deeper P and S waves. They are generated when those body waves reach the free surface of the Earth and interact with it, trapping their energy near the ground, much like the waves that form on the surface of the ocean after a stone is thrown in. But unlike ocean waves, these roll through solid ground. They travel more slowly than their parents, but they are larger in amplitude and far longer in duration. Their energy is not focused deep within the planet. It is concentrated right where we live, right under our feet and our foundations. There are two primary types of these waves, each with its own, uniquely destructive character. First, love waves. Named for the mathematician who discovered them, there is nothing loving about them. They are the first surface waves to arrive, and they move the ground from side to side in a horizontal, snake-like motion, perpendicular to the direction of travel. Imagine gripping a rug at both ends and sending a sharp, sideways ripple down its length. This shearing motion is devastating to building foundations, as it attacks the base of structures laterally, trying to slide them right off their moorings. Following the love waves come the Rayleigh waves. These move in a more complex way, rolling along the ground like waves on the sea. The ground moves in a vertical, elliptical motion, causing it to rise and fall and surge forward simultaneously. It is this motion that can make the ground appear to be moving in visible, liquid-like ripples. It feels like standing on a mattress that is being shaken at one end. This combination of vertical and horizontal motion places an immense, rocking strain on structures. A building that survived the sharp jolts and shearing might be rocked off its foundation by this prolonged, rolling sway. It is this duration that makes surface waves so uniquely dangerous. While the S waves deliver a sharp, brutal punch, the surface waves can last for minutes, relentlessly stressing and weakening structures. They can excite the natural resonance of large buildings, causing them to sway ever more wildly until they tear themselves apart. They are also the primary culprits behind the phenomenon of liquefaction, where the rolling pressure causes water-saturated soil to temporarily lose its strength and behave like a liquid, swallowing everything on top of it. The surface waves are the earthquake's finale. They are the long, drawn-out echo of the deep rupture, the energy that lingers at the surface to finish the work the other waves began. They carry the energy topple what was weakened, to collapse what was cracked, and to transform the solid, reliable earth into a rolling, treacherous sea. In the aftermath of the shaking, once the dust begins to settle and the rolling earth grows still, we are left with a single, pressing question. How big was it? We crave a number, a single value, to categorize the event, to give a sense of scale to the chaos. For decades, the name we've reached for is the Richter scale, but this famous scale is often misunderstood. It is more than just a number. It is a logarithmic key to unlocking the awesome energy released deep within the Earth. Developed by Charles Richter, in 1935 the scale was a revolution. It provided a standardized way to compare the size of earthquakes in California based on the wiggles, the amplitude, recorded on a specific type of seismograph. The concept is beautifully simple. Each whole number increase on the scale represents a tenfold increase in the amplitude of the seismic waves. But here is the crucial and often missed point. It represents a roughly 32-fold increase in the energy released. Let us sit with that for a moment. The difference between a magnitude 5.0 and a magnitude 6.0 quake is not a simple addition of 1. It is the difference between a small, contained explosion and one that is 32 times more powerful. A magnitude 7.0 quake releases nearly 1,000 times the energy of a 5.0. This is why the higher numbers on the scale are so fearsome. The scale is not linear, it is exponential, opening a vast gulf between whole numbers. But the Richter scale, for all its fame, has a limitation. It was designed for a specific region and a specific type of instrument. Today, seismologists use more precise and universal scales like the moment magnitude scale, MW, which calculates the total energy released by the earthquake based on the area of the fault that ruptured, the distance it slipped, and the rigidity of the rock. This is the number you see reported after major global quakes. It gives a more accurate, complete picture of the earthquake's true size, its magnitude. This is the first half of a vital distinction: magnitude versus intensity. Magnitude is like the wattage of a light bulb. It is a single number that describes the power at the source. A 100-watt bulb is always a 100-watt bulb, whether it's in a closet or a cathedral. Similarly, an earthquake has only one magnitude, value. Intensity, however, is like the brightness of that light in a particular room. It depends on distance from the bulb, the presence of lampshades, the color of the walls. Intensity measures how strong the shaking was at a specific location. It is shaped by the earthquake's magnitude, but also by your distance from the epicenter, the depth of the quake, and the local geology. The same magnitude 7.0 quake will feel like a violent, destructive event near the epicenter, but might only be a gentle swaying motion hundreds of miles away on solid bedrock. So the next time you hear a magnitude number, hear the story behind it. It is not just a digit. It is a logarithmic whisper of the immense forces at work deep below, a calculation of the planet's expended energy. It is the first, but not the last, word in understanding the earthquake's reach. A single number, the magnitude, tells us the power of the earthquake at its source, but it cannot tell us the human story. It cannot tell us if the shaking was a gentle rumble that barely rattled the china or a violent convulsion that toppled buildings. For that we need a different scale, one that listens to the Earth's impact on us. This is the modified Mercalli intensity scale. It doesn't measure the earthquake's energy, but its effect. Unlike the Richter scale, which gives one number for the entire event, the Mercalli scale produces a map of many numbers. It is a detailed, qualitative portrait of the shaking, painted from countless human observations and reports of damage. It answers the question, what did people experience and what did the earthquake do here? The scale is expressed in Roman numerals from I to tutti, and it reads like a narrative that grows increasingly severe. It begins at eye, not felt. The earthquake is detected only by sensitive instruments. The world is still. It progresses to 3. Weak, felt noticeably, indoors, like the vibration from a passing truck. Hanging objects may swing slightly. By V, moderate, almost everyone feels it. Sleepers are awakened. Doors swing open and shut. Dishes rattle. Small, unstable objects may be overturned. This is where the disturbance moves from curiosity to disruption. C. Strong is a turning point. It is felt by all. People may have trouble walking steadily. Damage is light. Plaster may crack. Windows break. Furniture moves. The environment reacts. Trees may be seen shaking. 7. Very strong brings significant damage to poorly built structures. Everyone runs outdoors. Driving a car becomes difficult as the shaking is unmistakable. Bells on churches may ring. The scale climbs into true destruction with 8. Severe and nigh violent. Partial collapse of ordinary buildings, substantial damage to even well-designed structures, foundations shift, underground pipes rupture. The ground itself begins to crack. At the peak, X, extreme, and Toost, extreme, the landscape is altered. Most masonry and frame structures are destroyed. Rails bend. Large landslides occur. The ground is scarred with broad fissures. Objects are thrown into the air. The destruction is total. The beauty of the Mercalli scale is its humanity. It is built from thousands of stories. Did the church bells ring? Did the chimney fall? Could people stand? These personal accounts, gathered from across the affected region, allow seismologists to create a detailed, shaking map that shows how the earthquake's intensity faded with distance from the epicenter and how it was amplified in areas with soft, loose soils. So, while magnitude tells us the size of the bell that was struck, the modified Mercalli scale tells us how loudly it rang in every town, on every street, and for every person who felt the world move. In the stillness of a vault, deep in the heart of an observatory, or buried in a quiet basement, a sentinel keeps watch. It is an instrument of profound patience, designed to listen for a conversation that happens in a language of force and vibration. This is the seismograph, the ear we press to the ground to hear the earth's deepest whispers and loudest shouts. At its heart, the principle is beautiful in its simplicity. How do you record the movement of the very ground upon which you stand? The solution is inertia. A heavy mass, suspended by a spring or wire, wishes to remain still due to its inertia. The frame of the instrument, bolted to the earth, moves with the tremor. But the suspended mass lags behind, resisting the motion. In the earliest seismographs, this relative motion was magnified by a series of levers and recorded by a stylus scratching a line onto a cylinder of smoked paper that rotated slowly on a clockwork drum. Every gentle vibration, every violent jolt was translated into a permanent record, a seismogram. This delicate scribble is the earthquake's signature, its fingerprint pressed into paper. Modern instruments are digital, using electromagnets and electronic sensors to achieve the same principle with breathtaking sensitivity. They can detect the rumble of a truck miles away, the crash of ocean waves on a distant coast, and the footfall of a person walking nearby. But their true purpose is to feel the far-off shudder of a fault line slipping hundreds or thousands of kilometers away. When the Earth is still, the stylus, or the digital sensor, draws a nearly straight, quiet line. This is the heartbeat of a calm planet. But when seismic waves arrive, this quiet line comes to life. The first tiny, frantic zigzags are the fast-moving P-waves, the eager messengers. Then the larger, wilder swings begin as the S-waves arrive. Their greater amplitude scrawling a wider, more destructive path across the page. Finally, the long, rolling, high-amplitude waves, the surface waves, arrive, drawing great, looping circles that can dominate the record for minutes. A seismologist can read this scribble like a historian reads an ancient text. The spacing of the waves reveals their type. The amplitude of the squiggles tells of the energy released. The timing of their arrival pinpoints the distance to the epicenter. From this single, intricate tracing, the entire story of the distant earthquake can be reconstructed. This instrument transforms the intangible of vibration into the permanent and tangible. It turns force into a document. It is a bridge between our world and the immense, hidden forces that shape it. In its quiet vault, the seismograph does not sleep. It listens endlessly, recording the planet's every sigh and tremor, a faithful scribe to the Earth's restless soul. The main shock has passed. The violent crescendo of seismic waves has rolled through and faded away. But the Earth does not simply fall silent. In the minutes, hours, days, and even years that follow, the ground continues to speak. Not with the same roaring voice, but with echoes. These are the aftershock, the planet's way of settling its accounts, of finding a new, fragile equilibrium after the colossal release of a great earthquake. An earthquake is not a single, clean break. Imagine a vast old bookcase overstuffed and heavy. For years it stands still, but the weight and strain slowly warp its frame. Then one day, one key joint gives way. The entire structure lurches, shelves shift, and books tumble. But it does not come to rest immediately. It settles, it groans. Other overstressed joints, now bearing weight in new ways, may snap in turn. Each of these smaller adjustments is an aftershock. Scientifically, the main shock violently redistributes stress along the fault and in the surrounding crust. Some areas are left holding more strain than they can bear. Aftershocks are these smaller patches of rock suddenly failing under this new, transferred pressure. They are the fault system's attempt to smooth out the rough edges of the new reality the main shock has created. They follow a predictable, yet unsettling, pattern. The largest aftershock is usually about 1 magnitude unit smaller than the main shock. They become more frequent immediately after the main event, then gradually decrease in both number and size over time. This fading sequence can last for decades, a long tail of reminders. For those who have lived through the terror of the main quake, each aftershock is a cruel jolt of adrenaline, a trigger that brings the fear rushing back. It is the psychological torture of the event, making it impossible to feel safe, to trust the solidity of the world just yet. But for seismologists, these echoes are invaluable. The pattern of aftershocks helps map the extent of the fault that ruptured. Each small tremor is a clue, illuminating the hidden architecture of the fracture deep underground. They are the Earth's own data points teaching us about the stresses that shape our world. Aftershocks are the planet's long sigh of adjustment. They are the sound of the Earth rearranging its furniture after a violent event, a process that requires patience and time. They remind us that an earthquake is not a moment, but a process, a chapter that begins with a cataclysm and ends only when the last faint whisper of movement finally fades into silence. We think of the ground beneath our feet as the ultimate symbol of stability, but in the violent grip of an earthquake, this most solid of things can undergo a terrifying transformation. It can, in essence, become a liquid. This is not magic or myth. It is a deadly geological phenomenon known as liquefaction, and it is one of an earthquake's most bizarre and destructive tricks. To understand how solid ground can turn to soup, we must look at what soil is made of. In many places, especially near rivers, lakes, and coasts, the ground is not solid rock. It is a mixture of loose, granular sand, silt, and soil particles, and in the spaces between these particles, there is water. Under normal conditions, the contact between the particles creates friction, locking them together and giving the ground its strength. It feels solid because it is solid, but an earthquake's prolonged shaking, particularly from those rolling surface waves, changes everything. The vibration violently agitates the water-saturated soil. The particles are jostled and begin to lose their frictional contacts. They try to move into a more densely packed arrangement, but this increases the pressure on the water trapped between them. Imagine a jar filled with sand and water. If you tap the jar gently, nothing happens. But if you shake it vigorously and suddenly stop, the sand appears to liquefy for a moment, becoming a slurry before the particles settle again. An earthquake provides that violent, sustained shaking on a massive scale. The water pressure builds so dramatically that it effectively pushes the soil particles apart. The ground temporarily loses its strength and behaves like a dense fluid. The consequences are surreal and devastating. Buildings, roads, and pipelines, which were resting on solid ground, suddenly find themselves floating in or sinking into a viscous slurry. They can tilt and sink unevenly. Underground tanks and sewer lines, now buoyant, can suddenly pop up out of the ground. Most eerily, the phenomenon can reverse itself. When the shaking stops, the water pressure gradually dissipates the soil. Particles settle back into contact, and the ground becomes solid again. But it is now a landscape frozen in the moment of its failure, with structures tilted, buried, or collapsed. Liquefaction is a powerful reminder that our world is not always as it seems. The earth we build upon can hide a hidden fragility, a latent liquid state waiting for the right tremor to reveal it. It is the moment the planet's solid stage dissolves, proving that even the ground itself can lose its composure under the immense and relentless language of seismic force. Japan and the Indonesian islands are all born from this relentless process of subduction. Each majestic, cone-shaped peak is a vent, a release valve for the planet's immense internal pressures. But the fire is only half the story. The same subduction process that creates volcanoes is also the source of the ring's infamous earthquakes. As the descending oceanic plate grinds against the overriding plate, they become locked together by friction. Stress builds over decades or centuries, until it is finally released in a sudden, catastrophic slip. This is the mechanism behind the most powerful earthquakes on Earth, the megathrust events. The 2011 Tohoku earthquake in Japan, which unleashed a devastating tsunami, and the 1960 Great Chilean earthquake, the strongest ever recorded, both originated in the tortured subduction zones of the Ring of Fire. The ring is not solely defined by subduction. In places, it is also stitched together by transform boundaries, where plates slide past one another. The San Andreas Fault in California is the most famous example, a place where the Pacific plate grinds northwards against the North American plate, not with a collision, but with a sideways grind that produces its own distinctive and powerful earthquakes. And in the southwestern Pacific, the ring features zones of divergence, where plates are pulling apart. The Tonga-Kermadec Trench is one of the fastest subduction zones on Earth, but nearby, the sea floor is also ripping apart, creating new crust and adding another layer of complexity to this geologically dynamic region. To take a tour of the Ring of Fire is to witness the planet's most dramatic geology on a grand scale. We would begin in the Andes of South America, where the Nazca Plate plunges beneath the continent, creating a breathtaking backdrop of volcanic peaks for cities like Quito and Santiago, and generating earthquakes that periodically reshape the land. Journeying north, we would encounter the relatively quiet but potentially dangerous Cascadia subduction zone off the coast of the Pacific Northwest. Here, the Juan de Fuca Plate is subducting beneath North America. It is a fault line that sleeps for centuries, but when it awakens, it can produce earthquakes that last for minutes and generate tsunamis that cross the entire Pacific. Our tour would continue through the Aleutian Islands of Alaska, a string of volcanic islands formed by the Pacific Plate subducting beneath the North American plate, one of the most seismically active regions on the continent. From there, we cross into the Kuril Islands and Japan, the heart of the Ring of Fire. Japan is a nation built upon the geologic consequences of subduction, home to over 100 active volcanoes and constantly monitored by a network of seismometers, a society that has learned to respect and adapt to the tremors beneath its feet. The ring continues through the Philippines, a complex jigsaw puzzle of tectonic microplates, resulting in frequent and often devastating quakes and a stunning landscape dotted with iconic volcanoes like Mayon. We then travel through the Indonesian archipelago, where the Indo-Australian plate subducts beneath the Eurasian plate. This is the realm of Krakatoa and Tambora, volcanoes whose historic eruptions changed global climates, and the source of the immense 2004 Indian Ocean earthquake and tsunami. Finally, our circuit completes in New Zealand, which straddles the boundary between the Pacific and Australian plates. Here, the tectonic drama is visible everywhere, from the soaring southern Alps thrust up by the collision to the transform boundary of the Alpine Fault, which slices across the South Island and is one of the world's most studied and most anticipated fault linings. To live on the Ring of Fire is to understand a fundamental truth about our planet, that creation and destruction are two sides of the same coin. The same forces that build magnificent mountain ranges and fertile volcanic soils can, in an instant, bring unimaginable devastation. The Ring of Fire is a testament to the Earth's dynamic nature, a constant, humbling reminder that we are merely guests living on the surface of a profoundly active world. It is a landscape of breathtaking beauty, forged in fire and tempered by tremor. While the Ring of Fire tells a story of collision and consumption, there is another, equally profound narrative unfolding on the other side of the globe. This is a story not of continents crashing together, but of a continent slowly, patiently, tearing itself apart. This is the Great Rift of Africa, a place where we can witness the breathtakingly slow birth of an ocean and feel the deep, stretching, growing pains of a planet reshaping itself. Imagine a place where the very fabric of a continent is under tension. For millions of years, enormous thermal currents rising from deep within the Earth's mantle have been pushing upward beneath eastern Africa. This upward pressure causes the vast continental plate to dome upward, and critically, to stretch. The crust, like a piece of taffy pulled from both ends, becomes thinner and thinner until it finally cracks. This is the essence of a continental rift valley, not a scar from a collision, but a crack from a pull. The East African rift systems are a massive network of these cracks, a Y-shaped fracture stretching over 3,000 kilometers from the Red Sea down to Mozambique. It is a living laboratory for the earliest stages of plate tectonics. Here, the African plate is not colliding with another. It is actively splitting into two new plates, the smaller Somali plate and the larger Nubian plate. This process measures in millimeters per year, a pace so slow it is invisible to our eyes but unmistakable over geologic time. The landscape this process creates is one of surreal beauty and dramatic contrast. The rift is not a single canyon, but a series of linked valleys, each known as a graben. These are blocks of crust that have dropped down between parallel faults as the land stretches apart. Between these valleys stand towering shoulders of uplifted land called horsts. This creates a world of deep, flat valleys flanked by sheer escarpments and high plateaus. It is a terrain of verticality, a direct testament to the powerful forces of extension. Within this torn landscape, the Earth's inner workings are laid bare. The thinning crust allows magma from the upper mantle to rise much more easily towards the surface. This is why the Rift Valley is dotted with some of Africa's most iconic volcanoes, Mount Kilimanjaro, Mount Kenya, and the simmering lava lake of Mount Nyiragongo. The geothermal activity is intense, with hot springs and geysers steaming along the valley floor, a direct venting of the Earth's inner heat. And of course, where there is stretching, faulting and slipping rock, there are earthquakes. The seismicity of the East African Rift is different from the violent megathrust quakes of the Ring of Fire. Here, the earthquakes are generated by normal faults. As the crust stretches, these faults slip, with one block of crust sliding down relative to another. These quakes tend to be shallower, and although often smaller in magnitude, they can be intensely felt and damaging to the communities living along the rift. They are not the sound of a collision, but the creak and groan of a continent slowly opening up. This great rift is also a cradle of life in more ways than one. The valleys have filled with water, creating deep, ancient lakes like Tanganyika and Malawi, which are home to unique ecosystems that evolved in isolation. The volcanic ash has enriched the soils, creating fertile grounds for life and for human agriculture. It is no coincidence that some of the earliest hominid fossils have been found in the sediments of this rift, preserved in its layers. Humanity itself in many ways began in this geologic nursery. To stand in the Great Rift Valley is to stand on the edge of a future ocean. If this rifting continues for tens of millions of years, the land will stretch thin enough for the sea to flood in, just as it did with the Red Sea. Somalia and a piece of Eastern Africa will drift away, becoming a new continent, a new Madagascar. On a grand scale, we are witnessing the very first chapter in the story of a new ocean. The Great Rift is the planet's patient masterpiece. It is a reminder that the Earth's most transformative work is often done not in sudden cataclysms, but in a slow, persistent pull. It is a landscape of creation, born from the profound and simple act of breaking apart. There are places on Earth where the planet's restless energy is written not in subtle cracks or slow pulls, but in the most spectacular and monumental of scripts. The Himalayas are such a place. This is not a landscape of quiet growth, but one born from the most colossal collision imaginable. It is an ongoing car crash in slow motion, a geologic event of such staggering scale that it has raised the highest points on our planet and continues to fuel some of its most powerful earthquakes. The story begins not with mountains, but with an ocean. Around 50 million years ago, the vast Tethys Ocean separated the ancient continent of Gondwana from the northern land masses. India, a continental fragment broken off from Gondwana, was adrift, racing northwards at a geologically furious pace, some 15 centimeters a year. As it moved, the Tethys Ocean floor ahead of it was consumed, subducting beneath Asia. Then the inevitable happened. The ocean closed. The last of the oceanic crust vanished into the mantle. And India, a continent of buoyant, lightweight rock, could not follow. It slammed into the southern underbelly of Asia. In a collision between two continents, neither is dense enough to subduct easily. There is only one possible outcome. The crust must go somewhere. And so it went up. The force of the impact was incomprehensible. Layers of rock that had once lain flat on the ocean floor were crumpled, folded, and thrust skyward like wrinkles in a rug pushed against a wall. The Himalayas were not built gently. They were forged in a violent, slow-motion collision that continues to this day. India is still pushing north into Asia at a rate of about 2 inches a year, and the Himalayas are still rising, growing by a few millimeters each year, even as erosion tries to wear them down. This relentless, ongoing collision is the engine for immense seismic activity. The entire region is a vast, complex network of faults, all absorbing the incredible stress of this continental wreck. The main boundary is the main Himalayan thrust, MHT, a massive fault that is the primary plane of contact where the Indian plate is diving beneath the Eurasian plate. This is not a smooth process. The plates become locked together by friction for decades or even centuries. The Indian plate continues to push, but the Eurasian plate above it is held fast. During this locked phase, the entire region becomes a spring being compressed. The land itself is deformed. The mountains are squeezed, the crust is strained, and incredible amounts of energy are stored. This can continue for centuries, but rock can only bend so far. Eventually, the stress becomes too great. The friction locking. The fault fails catastrophically. The fault slips and the pent-up energy is released in seconds. The land that was being compressed suddenly lurches and the earth roars. This is the source of the great Himalayan megathrust earthquakes. The earthquakes here are particularly devastating because they are shallow. The rupture occurs close to the surface, so their energy is focused and intense, shaking the ground with terrible violence. The 2015 Gorkha earthquake in Nepal, which killed thousands and leveled entire villages, was a tragic reminder of this ongoing tectonic struggle. It was not a random event, but a single, violent adjustment in a collision that has lasted 50 million years. To look upon the Himalayas is to see the direct result of an earthquake that has been happening for millennia. Every peak, every ridge is a monument to tectonic force. The folded layers of rock exposed in the cliffs, the fossilized seashells found on high summit slopes, they all tell the story of this epic collision. The mountains themselves are the earthquake, frozen in stone and lifted to the sky. The Himalayas remind us that the most beautiful and awe-inspiring landscapes are often born from violence. They are a permanent, towering record of the Earth's power, a testament to the fact that even the mightiest of mountains are simply temporary features in the endless, slow, and powerful dance of the continents. We have learned to expect the Earth's tremors at its seams, along the crashing boundaries of its great tectonic plates. The Ring of Fire, the Himalayan front, the grinding faults of California. These are the expected stages for the planet's seismic performances, but sometimes the script is flipped. Sometimes the solid, seemingly immutable heart of a continent itself begins to shudder. These events are called intraplate earthquakes, and they are among the most enigmatic and unsettling of all seismic phenomena. An intraplate earthquake is, by definition, a paradox. It occurs in the middle of a tectonic plate, far from the active, grinding edges where we know the Earth is in constant motion. It is a tremor from the quiet rooms of the house, not the noisy doorways. For centuries, these quakes were geological mysteries, seemingly coming from nowhere, defying the elegant logic of plate tectonics. The most famous example in North America is the New Madrid seismic zone. Located in the central United States, far from the Pacific or North Atlantic boundaries, it was the source of some of the most powerful earthquakes ever recorded on the continent. In the winter of 1811-1812, a series of 4 catastrophic quakes, estimated at magnitudes above 7.0, struck this region. The force was so great that church bells rang in Boston, over 1,000 miles away. The Mississippi River reportedly ran backwards, and the land itself was warped, with new lakes formed and whole forests sunk beneath the water. How can this be? How can the stable core of a continent, a place that hasn't seen mountain building in hundreds of millions of years, suddenly unleash such fury? The answer lies in the past. The Earth has a long memory. These intraplate quakes are often the ghosts of ancient tectonic events. The New Madrid zone, for instance, is thought to be a buried, failed rift, or Aulacogen. Hundreds of millions of years ago, the continent tried to split apart here. The process began, but then stopped, leaving behind a network of deep, ancient faults like old scars in the basement rock. These old weaknesses never fully heal. The immense weight of the continent above keeps these faults locked. But over millions of years, the entire plate is subject to broad, regional stresses transmitted from the distant, active boundaries. The plate may be moving over a slight bump in the mantle, or the crust may be slowly rebounding after the retreat. of massive ice sheets from the last ice age. These subtle, pervasive forces slowly accumulate strain, and eventually that strain finds a release valve in one of these ancient zones of weakness. The old fault reactivates, and the stable interior is jolted by a reminder of its violent past. The unsettling aspect of intraplate quakes is not just their location, but their impact. Because they occur in regions where earthquakes are not expected, building codes are often less stringent. The geology of stable interiors can also amplify shaking tremendously. The deep, soft sediments of river valleys like the Mississippi Basin can act like a bowl of jelly, shaking far more violently than the hard rock at the epicenter. A moderate intraplate quake can therefore cause damage disproportionate to its magnitude, from the seismic zones of Charleston, South Carolina, to the ancient faults beneath western India that caused the devastating 2001 Bhuj earthquake. These events are a crucial reminder. They tell us that no place on Earth is ever truly geologically silent. The plates are not rigid, unchanging slabs. They are constantly, if imperceptibly, flexing and straining under pressure from all directions. The Earth's memory is long and its weaknesses are permanent. An intraplate earthquake is a message from the deep past, a sudden recollection of an ancient trauma written in the planet's very foundations. It is the ground beneath our feet reminding us that even in the most tranquil of places we are still living on a dynamic, restless world where the ghosts of old geology can awaken without warning. Of all the questions that follow the shaking, one lingers longest, echoing through the halls of science and in the hearts of those who live in tremors' shadow. Can we predict them? Is it possible to know when the Earth will speak? To translate its restlessness into a specific time, a specific place, a specific magnitude? The yearning for this knowledge is ancient and profound. But the answer, whispered from the frontiers of seismology, is a gentle, steadfast no. Earthquake prediction, in the way we might hope for, remains the field's elusive and likely impossible goal. To predict an earthquake would require three precise pieces of information: the location, the time, and the magnitude of the impending event. Modern science cannot provide this. The Earth does not give up its secrets so easily. The fault systems that generate great quakes are hidden deep underground, fantastically complex, and governed by the laws of chaos. The final trigger, the tiny grain of rock that gives way to start the catastrophic rupture, is as random and unpredictable as the single snowflake that starts an avalanche. For decades, scientists have searched for reliable precursors, measurable. Phenomena that would signal an earthquake is imminent. They have investigated everything from the strange behavior of animals and the levels of radon gas seeping from the ground to subtle changes in the Earth's magnetic field and the electrical properties of rocks. While intriguing anecdotes abound, no single precursor or consistent set of precursors has ever been proven to reliably occur before a major quake. What might happen before one earthquake may not happen before the next. The Earth does not always send a clear warning. The fundamental challenge is that the Earth's crust is in a state of criticality. Imagine building a house of cards higher and higher. You know it will collapse, but you cannot predict which breath, which tiny vibration will be the one to bring it down. You cannot know which card will slip first. The fault system is like that house of cards. Stress builds to a critical point. The system is poised for failure, but the precise moment of failure is governed by countless tiny, unmeasurable factors. This does not mean that seismology is helpless. Far from it. While we cannot predict, we have become remarkably skilled at forecasting. This is a crucial distinction. Prediction would be a magnitude 7.0 earthquake will occur on the Hayward Fault tomorrow at 3:15 p.m. Forecasting is over. The next 30 years, there is a 72% probability of a magnitude 6.7 or larger earthquake on the southern San Andreas Fault. Forecasting deals in probabilities over long timescales based on the historical record of quakes and the measured rate of strain accumulation. It is a statistical warning, not a precise prophecy. Furthermore, we have mastered early warning. This is not prediction, but rapid response. Using networks of seismometers, we can detect the fast-moving but harmless P waves the instant an earthquake begins. Computers then calculate the expected intensity and send out alerts before the slower, destructive S waves and surface waves arrive. This provides precious seconds, sometimes a minute or more, to automatically stop trains, halt surgeries, and allow people to brace for impact. It doesn't predict the quake, it outruns it. The quest for prediction continues, not with the goal of a crystal ball, but with the hope of better understanding the intricate physics of fault failure. It is a pursuit that requires humility. It forces us to accept that our planet operates on a scale of complexity that we may never fully unravel. The earthquake remains, in its final moment, a profound mystery. Perhaps this is not a failure, but a lesson. The impossibility of prediction is a reminder that we are not separate from nature, but a part of it, living on a dynamic, unpredictable planet. It shifts our responsibility from a futile search for a specific warning to the practical, achievable work of preparation, building resilient communities, constructing flexible structures, and creating robust warning systems. We may never know exactly when the Earth will move, but we can always know how to be ready for when it does. In the long, uncertain shadow of the unpredictable, science has carved out a sliver of certainty. It cannot tell us when the earthquake will begin, but it can tell us that it has begun, and it can deliver this message faster than the earthquakes. Own waves can travel. This is the power of early warning, a technological symphony that turns seconds into a sanctuary, offering a precious and potentially life-saving head start. The principle is breathtakingly elegant. It leverages a simple fact. Different seismic waves travel at different speeds. The initial rupture at the hypocenter generates energy that radiates outward in all directions. The first to arrive are the P waves, the primary waves. These are fast, but they are also relatively weak, causing a sharp jolt but little damage. They are the messengers. Trailing behind them, moving at about half the speed, are the S waves, the secondary waves. These are the carriers of the earthquake's destructive power, the violent shearing motion that collapses buildings. And following them, the slowest but most devastating of all, the surface waves that roll across the landscape like a tide of ruin. An earthquake early warning system is a network of thousands of sensitive seismometers planted directly onto the Earth's skin, often along major fault lines. These are the system's nerve endings. The moment an earthquake begins, the closest seismometers detect the faint initial signature of the P waves. In a fraction of a second, this data is relayed to a central processing center. Algorithms, honed by decades of research, instantly analyze the tiny wiggles. They calculate the earthquake's location, its depth, and, crucially, its estimated magnitude. They then predict the intensity of shaking that will follow across the region. This entire calculation happens in less than 2 seconds. Then the system performs its most vital task. It races the waves. It sends out an alert, a digital shout, that travels at the speed of light through fiber optic cables and cell networks. This alert can outpace the destructive S waves, which are still lumbering through the bedrock at a mere 3.5 kilometers per second. The warning might give you 10 seconds, it might give you 60. The further you are from the epicenter, the more time you get. It is not a lot of time, but it is enough. It is a moment of grace in the chaos. In those seconds, automated systems can spring to life. Trains can trigger their emergency brakes, preventing derailment at high speed. Elevators can command their cars to stop at the nearest floor and open their doors. Gas lines can automatically shut their valves, preventing catastrophic fires. Surgeons can lift a scalpel from a patient's body, Fire station doors can swing open, ensuring first responders aren't trapped inside. For individuals, the alert is a call to action. A phone screen lighting up with a distinct, piercing sound. A public siren blaring a specific tone. Those few seconds are enough to mentally switch from confusion to purpose. It is enough to drop, cover, and hold on, to move away from windows, to wake a sleeping child and pull them under a table. It is the difference between being caught standing in a shower of glass and being safely braced in a doorway. But these systems are not omniscient. They are a race against physics, and sometimes the finish line is too close. For those near the epicenter, the warning may arrive only as the shaking begins, or even after. This is the tragic irony. Those in the greatest danger may receive the least notice. The system is a shield for the surrounding region, not for the earthquake's ground zero. Countries like Japan and Mexico have refined this technology to an art form. Their public drills and integrated alert systems have saved countless lives. The warning does not stop the earthquake. It cannot prevent all damage, but it redefines our relationship with the inevitable. It transforms us from passive victims into active participants in our own survival. It is a testament to human ingenuity, our ability to listen to the Earth's first whisper and, in the blink of an eye, shout a warning to millions. It is the harnessing of light to outrun sound, of data to outmaneuver destruction. In those fleeting, precious seconds, we don't conquer the earthquake, but we learn to dance with it, finding our footing just before the floor begins to sway. We cannot stop the earthquake. The energy released from a fault rupture is orders of magnitude greater than anything we could hope to contain. For much of human history, our response to this power was to build heavier, stronger, and more rigid, hoping our structures could simply withstand the blow. This was a fight we often lost, but modern seismic engineering has undergone a profound philosophical shift. It is no longer about building fortresses to resist the Earth's motion. It is about designing structures that can dance with the waves, to yield, to flex, to absorb the energy, and to remain standing when the shaking stops. This is the art and science of designing for the tremors. It is an acknowledgement that we must work with the physics of the earthquake, not against them. The goal is not to prevent any damage, but to prevent catastrophic damage. To save lives by ensuring that buildings do not become tombs, that bridges do not become traps, that the very fabric of a city can endure the planet's pulse. The first and most revolutionary concept in this dance is base isolation. Imagine a building not as a rigid block fixed to the ground, but as a dignified figure standing on a rolling platform. Base isolators are bearings, often made of alternating layers of steel and rubber, placed between the building's foundation and the superstructure above. When the ground lurches sideways in an earthquake, these isolators flex and deform. They allow the foundation to shift dramatically beneath the building, while the structure itself sways gently and slowly, almost remaining stationary. The violent, high-frequency shaking of the ground is transformed into a slow, manageable rocking motion. The building is, in effect, decoupled from the worst of the earthquake's energy. It is granted a grace period. For taller, more flexible structures, a different strategy is employed: energy dissipation. These buildings are designed to have designated weak points, not weaknesses, but carefully engineered fuses. Devices like dampers are installed throughout the frame. Think of them as the shock absorbers of a building, massive piston-like. Dampers filled with thick fluid, or dampers containing yielding metal plates, are designed to absorb the seismic energy by converting it into heat and deforming themselves. As the building sways, these dampers take the brunt of the force, sacrificing themselves to protect the primary structural elements. They are the building's built-in sacrifice zones, ensuring the overall skeleton remains intact. The very materials and shapes we use have been reimagined. Ductile materials like specially designed steel and reinforced concrete are chosen for their ability to bend and deform significantly without suddenly snapping. A ductile frame will sway and crack in a controlled way, warning of its distress, while a brittle one will fail without notice. Shapes are simpler and more symmetrical to avoid uneven distributions of force that can cause a building to twist itself apart. We see this art all around us in seismically active regions. The Transamerica Pyramid in San Francisco is tapered to reduce wind and seismic loads. The Taipei 101 skyscraper in Taiwan features a massive tuned mass damper, a gigantic 660-ton golden ball suspended near its top that sways in the opposite direction of the building's movement, counteracting its motion like a pendulum. But this engineering is not just for skyscrapers, it is for hospitals, schools, fire stations, and homes. It is about retrofitting older, vulnerable structures, bolting unreinforced brick walls to wooden frames, adding steel braces to soft-story car parks, and strengthening crucial connection points. It is a continuous process of learning and adaptation. This is the quiet, profound work of resilience. It is a collaboration between geologists who understand the threat, engineers who design the solutions, and policymakers who prioritize safety. To build for tremors is to accept our place on a dynamic planet. We are not its masters, but its students. We are learning to move with it, to design a world that can bend without breaking, and to ensure that when the inevitable shaking comes, our shelters become our sanctuaries. The language of earthquakes is written in stress and strain, in seismic waves and magnitude. But when the shaking stops and the dust begins to settle, another story emerges. It is not written in the stone of faults or the steel of engineering, but in the human heart. This is the story that unfolds after the maps are drawn and the seismographs fall silent. It is the story of the spirit that rises from the rubble. In the immediate aftermath, the world is reduced to a terrifying simplicity. The intricate web of modern life, electricity, water, communication is severed. In its place, a raw, primal need takes over. Find loved ones, find safety, find water. The landscape is unrecognizable, a jumble of what was once home and haven. Yet, in this total loss of order, something profound happens. The artificial boundaries that divide us, stranger from neighbor, rich from poor, dissolve. Community is no longer an abstract idea. It is a survival strategy. The first responders are often not uniformed crews with heavy machinery, but the people who were there when the ground moved. The neighbor who hears a faint cry from under the porch and begins digging with bare hands. The shopkeeper who breaks into his own shattered store to bring out water and food. The doctor who sets up a triage center on a sidewalk with nothing but a first aid kit. This is the first and most powerful response to disaster. Not a top-down rescue, but a lateral web of mutual aid, a tapestry of care woven from the broken threads of a city, and then comes the long, slow work of recovery. This is not measured in seconds or days, but in months and years. It is the grueling physical labor of clearing debris piece by piece. It is the emotional labor of grieving what was lost while mustering the strength to rebuild. It is the psychological toll of every aftershock, a fresh tremor of fear running through a community already on edge. Yet within this struggle we see the most defiant acts of the human spirit. The library that opens in a tent amidst the ruins. The musicians who play in the central square to reclaim a sense of normalcy. The children who draw pictures of their old homes and their new hopes on scraps of paper. These are not small things. They are declarations that culture, identity, and joy are not luxuries for peaceful times, but essential tools for survival. They are the first foundations laid for the new world. We see this spirit echoed across the world and throughout history. In the ruins of Lisbon in 1755, where a devastating quake and tsunami sparked not just rebuilding, but profound philosophical debates about the nature of God and human suffering. In the flattened city of Messina in 1908, where international aid efforts forged new bonds between nations. In the bottle schools of Guatemala, built from recycled materials after the 1976 quake, becoming symbols of innovative resilience. In Japan, where the meticulous culture of preparedness is matched by a deep-seated communal obligation to care for one another. These stories tell us something crucial about who we are. The earthquake reveals our vulnerabilities, our fragility in the face of planetary forces, but our response to the earthquake reveals our strength. It reveals a capacity for empathy, sacrifice, and cooperation that is just as fundamental to our nature as the fear the tremor inspires. The process of rebuilding is, itself, a form of dialogue with the earth. We learn from the destruction. We improve our building codes. We rethink our urban planning. We remember which ground liquefied and which bedrock held firm. We do not just rebuild the same city. We try to build a wiser one, a more humble one, a city that has learned the steps to the earthquake's dance. The human spirit does not vanquish the earthquake. It cannot. But it does something perhaps more remarkable. It endures it. It finds light in the darkness, connection in the chaos, and meaning in the rubble. The final lesson of the tremor is not about the power of the planet to break things, but about the power of people to mend them. To stand in the rubble is to witness the end of one world and the difficult, courageous, and hopeful beginning of another. Throughout this journey, we have spoken of earthquakes in the language of human experience, as threats, as disasters, as events of fear and loss. This is a true and valid language, born from our immediate need for safety. But if we listen more closely, with a wider perspective, we begin to hear a different story. We hear that the tremor is not an anomaly. It is not the planet malfunctioning. It is the Earth's constant, necessary conversation with itself. It is the fundamental process by which a living planet regulates its energy, reshapes its face, and has ultimately made life itself possible. To understand this, we must step back from our human timescale. We must view the Earth not as a static stage upon which life unfolds, but as a dynamic, evolving entity. From this vantage point, and the earthquake is not a rupture of peace, but a punctuation mark in a billions-year-old narrative of transformation. It is the sound of the planet breathing. The engine of this process is plate tectonics. The Earth's interior retains a tremendous amount of heat from its formation and from the radioactive decay of elements within it. This heat must escape. It does so through the mantle's slow convective circulation, which drives the tectonic plates on their endless journeys. But this motion is not smooth. Plates stick, stress builds, and energy accumulates. The earthquake is the moment of release. It is the planet's way of venting this immense internal pressure. Without this release valve, the continuous buildup of stress would be catastrophic. The earthquakes, in their countless small adjustments, prevent a single world-shattering convulsion. They are the planet's safety mechanism. This process is the great sculptor of our world. Every mountain range that captures rain and creates rivers, every ocean basin that cradles marine life, every volcano that enriches the soil with minerals, all are the direct products of this tectonic conversation. The Himalayas, which generate the monsoon rains that feed billions, were built by a long series of unimaginably powerful earthquakes. The fertile soils of California valleys are weathered from rocks ground and uplifted by fault movements. The very continents upon which we live were assembled and are still being shaped by these occasional, violent adjustments. Earthquakes are also part of the planet's nutrient cycle. The grinding of plates recycles carbon and other essential elements from the crust back into the mantle and atmosphere, regulating long-term climate and geochemical cycles. They uplift ancient seabeds, rich in minerals, to become new land. They create new hydrothermal vents on the ocean floor, chemosynthetic oases that are likely where the first life on Earth began. The earthquake, in its most profound sense, is not just a symptom of a living planet, it is a catalyst for life. This reframing does not diminish the human tragedy. It does not ask us to welcome the shaking. Instead, it asks us to understand our place within a system far grander and more ancient than our civilizations. We are not living on a finished, stable product. We are inhabitants of a work in progress. The ground is not inert, it is active. The tremor is not an interruption of the norm, it is the norm on a geological scale. Our challenge, then, is not to curse the process, but to learn to live within it, to build with humility, to prepare with respect, and to listen to the geology of the places we call home. The earthquake reminds us that we are part of nature, not separate from it. Our cities are not built upon the earth. They are built within the Earth's active systems. The planet's constant conversation will continue with or without us. The plates will drift, the stress will build, and the energy will release. This is the price of a world with oceans and continents, with mountains and valleys, with a hot core and a dynamic mantle, a world capable of supporting life at all. The same forces that threaten our creations are the ones that created the stage upon which we built them. So the next time you feel the solid ground beneath your feet, remember, you are standing on the skin of a living, breathing, ever-changing world. The quiet is not permanent. It is a pause between sentences in a billion-year-old story. And the earthquake is simply the planet's deep, resonant voice, speaking the next word. We have journeyed together to the heart of the tremor, traced the lines of force deep within the earth, and felt the echo of its power in our own lives. We have learned the language of seismic waves and the architecture of resilience. And now, as we reach the end of our story, we are left with a single, quiet truth to carry forward. We live on a restless planet. This is not a statement of fear, but of fact. The ground beneath us is not a dead, static thing. It is alive with memory and movement, a dynamic system of breathtaking complexity and age. The earthquake is not an alien invasion of this system. It is its native tongue. It is the planet's pulse, a rhythm measured not in beats per minute, but in centuries of building strain and seconds of release. To understand this is to replace anxiety with awe, and to replace a desire for control with a practice of profound respect. We cannot command the tectonic plates to still their drift any more than we can command the tides to cease their pulling. Their motion is part of a planetary engine that long predates us and will long outlast us. This is not a cause for despair, but for liberation. It frees us from the illusion of domination and invites us into a relationship based on observation, understanding, and adaptation. Our role is not to conquer this restlessness, but to learn its rhythms, to build with flexibility, not rigid defiance, to listen to the geology of a place before we build upon it, to remember that the most stable-looking field might hide an ancient fault, and the most solid rock is capable of flow over millennia. This knowledge is not a burden, it is a gift. It is the wisdom that allows us to create societies that can endure, not by opposing the planet's nature, but by harmonizing with it. The restlessness of Earth is also the very reason for its beauty and its bounty. The same forces that generate earthquakes raise the mountains that catch the rain and create the rivers that water our civilizations. They churn the minerals into the soil that grows our food. They regulate the planet's temperature and recycle the elements essential for life. We are not living on a planet in spite of this dynamism. We are living here because of it. So, the next time you feel the ground beneath your feet, I hope you feel something new. Not just stability, but potential. Not just solidity, but a history. You are standing on the thin, cool skin of a world of fire and motion. You are connected to every other point on this globe by the invisible web of tectonic stresses and seismic waves. You are part of the conversation. The goal is not to live without fear, but to live with understanding, to know that the tremor is a part of the planet's story, and therefore a part of our own. This understanding is the ultimate form of resilience. It is what allows communities to come together after the shaking stops. It is what inspires engineers to design with genius and grace. It is what enables each of us to face the uncertainty of our planetary home not with dread, but with a steady heart. Our journey ends as it began, with a quiet corner, a slow unfolding, and a deep respect for the world as it is, not as we wish it to be. The Earth will continue its slow dance. Plates will drift, mountains will rise, and the crust will shudder as it releases its stored energy. This is not a problem to be solved. It is the nature of our home, and in that there is a strange and deep comfort. For all our knowledge, we are still creatures of this earth, subject to its rhythms and moved by its forces. To live on a restless planet is to remember that we are, and always will be, part of something vast, ancient, and magnificently alive. Thank you for listening, and sleep well.